Hello, my name is Gabriel Istrate, and I'm going to be presenting my paper on Kantian equilibria. So what are Kantian equilibria? They are a non-Nash equilibrium notion in finite games, whose clearest definition was given for a symmetric coordination game. They were defined by John Romer in the book shown on the left, and they're loosely based on the Kantian categorical imperative, act only according to the maxim, whereby you can at the same time will that it should become a universal law. So what that means is that all agents are assumed to play the same action, and the action that players are playing is the one chosen to maximize their common utility on the diagonal. So this presentation will deal with the philosophy of the results rather than the technical details of the results. So we're not going to present everything, both in terms of actual content and mathematical details. So why would we want to play something like a Kantian equilibrium? There are multiple perspectives under which this may be good. One of them is called superrationality, and it was studied by several people, most prominently Hofstadter, but also Howard and recently Fournier. So the basic idea is that in a symmetric game, if it is rational for one player to play an action X, then every other player can reach the same conclusion. Okay, and superrationality is actually more, it's quite heavy in terms of epistemic assumptions. It's even more restricting than a common knowledge of rationality, as Fournier has shown. A less demanding version, a justification for this would be the following. X is an action that, if played by all players, would be in some sense best for all. Now, several people have talked about synchronizing on an action in terms of so-called voodoo causation. Among these people, Sugden and Elser, but there is a way to present, to frame this idea that is quite intuitive. In that sense, agents have a utility which is decoupled from the actual payoffs they received. In other words, they don't really care about what the other people are doing. They care about what they are doing if everyone else was doing the same thing. So in a certain sense, playing the Kantian equilibrium is doing what's right. And people are using this type of universal arguments quite frequently, and there is recent empirical evidence for this fact. We're going to study Kantian equilibrium from a minimal rationality perspective, where we're looking for equilibrium notions that are easily implementable in agents that reason the way people reason like. So this puts some constraints on the kind of notions that we want to study. We want equilibrium notions that are expressive in the form that they model plausible interaction scenarios between people. They have to be computationally tractable. If it's hard to compute an equilibrium, then people aren't doing that. So this is, of course, related to Van Roy's tractable cognition thesis. They should also be cognitively tractable in the form of not requiring sophisticated epistemic assumptions from agents, things like common knowledge or many rounds of counterfactual reasoning, which people empirically are not good at doing. This can be formalized to a certain extent using recent notions developed by Solaki and Smets. And the main question we're interested in is the following. Are Kantian equilibria maybe suitably extended to more general games? A notion that satisfies such properties, or alternatively, are there other game-theoretic notions that satisfy some properties related to Kantian equilibrium and they're easier to implement? So the questions that I ask in this paper are the following, and I'm also going to give the intuitive conclusions. First of all, what's the complexity of Kantian equilibrium? Of course, they're very easy for pure Kantian equilibrium, but the moment we go to mixed Kantian equilibrium, and the moment we go beyond two-player symmetric coordination games, it is actually NP hard to compute them. Moreover, playing mixed Kantian equilibrium is problematic if multiple pure equilibria exist. The second question is the following. Can one define Kantian equilibria in more general games? Here the answer is yes, but not for general normal form games, but for a class of games, and I'm going to discuss this. The third question is, can one devise a notion that mixes Kantian and Nash equilibrium and interpolates between them? Here I have only the most limited of results, but the answer is yes, and I hope they're interesting enough to motivate further study. Finally, the question is, do we want to implement Kantian equilibria, or are there related notions better? My conclusion is that Kantian equilibria are theoretically interesting, but if you want to go to implementation, probably some versions of team reasoning are going to be more useful. So to start talking about mixed Kantian equilibria, I'm going to start with an example. So it's a so-called Platonia dilemma game defined first by Hofstadter. The idea is that n agents compete for a prize, and they can choose to submit their name to win the prize, or not submit them. And if exactly one agent will submit its name, it will win the prize. If more than one agent submits or no one submits, then everyone gets 0. Okay, so this is Platonia dilemma, and it's easy to see that pure Kantian equilibrium in this game are not terribly good, because everyone will get the 0. And of course, when we're looking for, so this motivates a study of mixed Kantian equilibria, and they're defined the way you would think they would be defined, as uncorrelated convex combinations of strategies. And they do a little bit better than pure Kantian equilibria, in the form that if everyone independently plays the strategy of submitting their name with probability 1/n, so that the expected number of people submitting is 1, then this is a mixed Kantian equilibrium. One can show this quite easily, and the expected payoff is strictly positive in this scenario. However, as I told you, the moment we go beyond two-player symmetric coordination games, we get into NP-hard problems. So the following problem is NP-hard. We're given a two-player symmetric game and an aspiration level, which is a rational number, and we want to decide whether there is a mixed strategy profile, such that if every player uses this profile, they are going to get payoff at least R. Okay. Now, to be really honest, there isn't much of a proof. It follows implicitly from results studied for a different problem in the literature. So I was able to connect the problem mixed Kantian equilibrium to a previously studied problem called quadratic optimization. And Motzkin and Strauss have shown the following fact, that if you take two-player symmetric games with 0-1 payoffs, which naturally correspond to graphs, then computing what would be called for us a mixed Kantian equilibrium is equivalent to computing a max clique in the equivalent graph, and of course that is intractable. So in a certain sense, mixed Kantian equilibrium fail already the tractability constraint that we wanted to impose on implementable notions. And there are other issues dealing with playing mixed Kantian equilibrium. So let's take the game on the left. It has two pure Kantian equilibrium. And for mixed Kantian equilibria, remember that a player is expecting that if it plays a strategy, then the other player is also going to play the same strategy. So one can talk about taking a convex combination of C and E under a Kantian scenario, and that would also be optimal. And if the players don't have a way to coordinate on one equilibrium, then they're perfectly justified to say play half C and half E. In fact, they're going to assume that they're going to play half CC and half EE because of the Kantian assumption. However, doing so would be bad. They're going to be worse off. In fact, they're going to be catastrophically worse off. Okay, if they play things in a mixed, uncoordinated fashion. And the paper has further framework and theorem that characterizes a price of miscoordination for Kantian equilibrium. The second game is this game on the right, where actually playing the same strategy is not good for the players. In fact, what they would like to do is anti-coordinate. They would like to perhaps play 50% of the time play the action profile CS, and 50% of the time play the action profile SC. Okay, so the conclusion of this argument, as well as a theorem about the price of miscoordination, that the meaningful extension of Kantian equilibrium is one where the notions assume that agents somehow coordinate. And of course, there are some connections to correlated equilibria you can see in the paper, but correlated equilibria are related to Nash equilibria, and we don't want our notion of Kantian equilibrium to capture also selfish behavior. So it's not going to be correlated equilibrium per se. Instead, we're going to go for a different ingredient, and that's the ingredient of program equilibrium. So as we've seen, intuitively, it would be even better in Platonian dilemma for the players to collectively implement the following protocol. They would choose among themselves one of the players uniformly at random, and that player is going to submit its name, and the other ones are going to not submit. So this is even better than the mixed Kantian equilibrium, and it can be implemented by agents all playing the same program. And the same is true for the anti-coordination game that we saw before, where players choose one bit and they use the XOR of their bits to basically choose an action to play, and they're going to be choosing it differently. We're going to break in symmetry by using agent ID as a part of the input for the program. So the conclusion of this argument is that to extend Kantian equilibria, we want some version of program equilibria. So program equilibrium is a concept introduced by Tenenholz, and using the same program is an intuitive way to formalize the fact that players are doing the same thing or taking the same action. So what is a program equilibrium? Program equilibrium was defined by Tenenholz. To any game, we associate an extended game whose actions are programs, and programs have access to the other agents' programs, and they can act accordingly. And the program equilibrium is simply Nash equilibrium of this extended game. So we would intuitively want to take the same idea of defining a Kantian program equilibrium through Kantian equilibrium of an extended game. Of course, this is only possible, first of all, when players have identical action sets, because those are going to be encoded in the program that all players are using. It's also the case that it's not clear what a program being best for all means in general for games that are not symmetric. So we're going to need to restrict ourselves to a class of games where this can be given a sense. Finally, a technical issue is that simply extending Tenenholz's formalization of programs will lead to paradoxical results, as in Kantian program equilibrium also capturing behavior that would be normally characterized as selfish. So essentially extending Nash equilibrium, which we don't want. So what we do is we restrict ourselves to a class of games with a certain symmetry, and the symmetry is quantified by having a group acting on the set of Pareto optimal action profiles in such a way that action profiles in the same orbit have the same multi-set of agent payoffs, and the expected payoff across of all the action profiles in one orbit of the action does not depend on the actual agent. So they're all going to get the same expected payoff. And I'm not going to formally define the notion of Kantian program equilibrium. It's somewhat technical. However, in the Theorem 10 in the extended version of the paper, I give a full characterization of Kantian program equilibria as convex combination of orbits that are maximizing expected payoffs for players. And this is good and intuitive for games such as the anti-coordination game we saw before, where the orbit consists of CS and SC. It's also good for things like Platonia dilemma, where the orbit consists of action profiles where exactly one player is submitting. And it's also good for prisoner's dilemma, where CC is its own orbit, and it's the best orbit to consider. The paper also considers comparisons between Kantian equilibria and other notions of equilibrium. One which is especially relevant is the notion of team equilibria. This was introduced by Michael Bachrach. And the basic idea is that sometimes agents go into a so-called team reasoning mode, which is characterized by a team utility the same for all players. In a certain sense, that's very close to the idea of taking the diagonal in Kantian games. Unfortunately, the notion of team equilibrium is not something that has a well-accepted formal definition. However, with a reasonably natural definition and one that is large enough, we can show that Kantian equilibria are a subset of team equilibria, a strict subset, because team equilibria also involve some actions where one player sacrifices itself, so it's not good for the player, but it may be good for the team. We also define several special kinds of team equilibria, which satisfy all the properties that we discussed in the introduction. They're tractable, they can implement some plausible scenarios, and furthermore, they relate to Kantian equilibria. So in special games, they can be shown that they get equilibria close to the ones that you get in the same games in Kantian equilibria. Finally, the last topic that I want to discuss is the issue of mixing Kantian and selfish behavior. This was attempted before by Alger and Weibull under the name of homo moralis. It was parameterized by a parameter lambda between 1 and plus infinity. And their definition has the following problem. A homo moralis agent, if it is not a Kantian one, then it will behave like a selfish agent. So it doesn't really interpolate between the two behaviors. We propose a different behavior, also parameterized by a parameter lambda. And the idea is that an agent will deviate from its Kantian action if it would obtain a payoff at least lambda times larger than the Kantian one. So if we rescale this parameter, we can define a degree of greed, and rational agents correspond to infinitely greedy agents, and Kantian agents correspond to zero greedy agents. And this definition has a nice consequence in prisoner's dilemma. We can justify all action profiles as equilibrium corresponding to agents with varying degrees of greed. Okay, so you can use the definition of greed as a way to eliminate some action profiles with minimal rationality assumptions. I haven't mentioned this, but in the rationality assumptions that we're using for the study are minimal in the form of just eliminating Pareto-dominated action profiles. To conclude, I hope that I convinced you that Kantian equilibria are a theoretically interesting notion that certainly deserves further study. Probably seeking more general definitions of Kantian equilibria is not the way to go if we're looking for an implementable notion. Finally, an open problem that I want to raise here, there are several other open problems in the paper, is that of coming up with a logical framework for Kantian games. And what I mean by that is that in our case, the payoffs were sort of given, and it would be interesting to have payoffs result from some sort of logical specification of the way a world is satisfying agent goals. Thank you.